Welcome back to eCoreAcademy, everyone. My name is Anita Raj, and I am one of the co-founders here, along with my younger brother, AJ Raj. As you can see, today we have a new Algebra 2 lesson, and we're going to be focusing on some inverse relations and functions practice problems. In the last 3 videos, we did some more instruction on what are inverses, how do we find them, and then we looked at several different problems, I think about 6 concerning inverses, that you're going to see but applied in different ways and probably more challenging ways on any homework assessments or anything you do in class regarding this unit, this lesson. So today we're going to be looking at inverse practice problems, and this is going to be part 1 of 2 pretty brief videos I'm going to make, just running through some practice problems, common ones I saw on my homework and assessments, and we're just going to be walking through our approach and then how we'd find the correct answer. So today specifically we're going to be doing 4 practice problems. These practice problems are going to obviously concern finding inverses from a relation or function that we've been given, then graphing these functions and inverses, then determining the domains and ranges of the functions and inverses, and then finally deciding if the inverse that we found is a true function, meaning is the domain continuous, and when we graph that inverse on the coordinate plane, does it pass the vertical line test? So these are the things we're going to be covering in this video, and then we'll cover 5 more practice problems in the next video. Before I get into the video, I would really appreciate it if you all could like, subscribe, hit the post notification bell, drop a comment down below, and share using all of our socials. Thank you, and let's get right into the video with our first practice problem. This practice problem is going to be on finding an inverse from a table, an XY table of values we've been given, finding the inverse from that relation, and then graphing both the relation, the original relation, and the inverse. So here's the problem. Find the inverse of the relation that I'm going to be showing you, and then graph the given relation and its inverse. Here is the XY table containing the points that are in this relation. Remember, a relation is pretty much just a relationship between 2 sets of numbers. In this case, it's going to be your domain, which are your x coordinates, and then your range, which is your y coordinates. A relation is pretty much when an x coordinate corresponds to a y coordinate. So one element of the first set corresponds to another element of the second set, as we learned in the past 3 videos. So in this case, these x, y coordinates pair up together to give you coordinate pairs. So for example, 1, 0 is a coordinate pair that belongs in this relation. So this is the relation we've been given. What we're asked now is, can we find its inverse? And then after we find the inverse, can we graph both the original relation and the inverse on the coordinate plane? So here's your solution. I'm just going to show you right now. Here's your XY table for the inverse. I'll run through how to find it, but I'm pretty sure you all will know how we find this XY table. And then here's the graph of both the function of the relation and its inverse. So let's walk through quickly, how are we going to find this? So here's your XY table. So how are we going to determine what points go under X and what points go under Y? Well, in this case, when we're asked to find the relation, when we've been asked to find the inverse, what we've been given is the relation. And in this case, the relation is not a function that we have like concrete knowledge about. We're not certain if this is a function. All we've been given are 4 coordinate pairs. So to find the relation, we don't need to try to find the equation to find the inverse, we don't need to find the equation of the inverse. All we need to do is just make an XY table and then graph this on the coordinate plane. So what we do is, if you remember, a relation or function we've been given originally, the x coordinates can be denoted as a and the y coordinates can be denoted as b, and then the relation is pretty much the coordinate pair a, b. To find the inverse, all we do is we reassign the x coordinates as b, and then the y coordinates become a, so we're pretty much just swapping the coordinate pair and making it ba. So in this case, literally all we're doing is taking the x coordinates of the original relation, making them the y coordinates of our inverse, taking the y coordinates of the original relation and making them the x coordinates of the inverse. So I'm going to write all the values in the x coordinate column of the relation under y here. So there's going to be 1, 2, 3, and 4. Then I'm going to take the y coordinates here and write them underneath the x column. So 0, 1, 2, and 3. So we found the inverse, and now what we have to do is we have to graph them on a coordinate plane. So let me quickly erase this because we already know the answer. Now we're going to actually graph these points on the coordinate plane. So the points of the original function were 1, 0, so that would be right here. So first, we're going to plot the original relation, of course. Make sure you don't use the terms relation and function interchangeably. I know because I'm speaking, I'm kind of doing that, but make sure you're not using those terms interchangeably. So we plotted the first point of the relation, which was 1, 0. I'm just reading off of the xy tables we were originally given in the problem. Then our next point in this relation was 2, 1. So that would be here. Our third point was 3, 2. You can see this is kind of forming a linear equation that looks like y equals x minus 1. We can't assume it's an equation, so we're just going to keep calling it an inverse. And then the last point was 4, 3, which was right here. What you can do is pretty much you can just connect these dots like that. And then what we're going to do is we're going to graph the inverse. So the inverse, I'm just reading off of that xy table that we just made. It's going to be 0, 1, which is right here. The next point is 1, 2. The third point is 2, 3. And the fourth point is 3, 4. I also want you to notice, well, now that we're done the problem, we can just connect these points and we have our inverse and our original relation graphed. But I want you to notice how the axis of symmetry is still y equals x. This line right here. This linear equation is still the axis of symmetry. The relation was pretty much just reflected across this axis of symmetry to give you the graph of its inverse. So that was problem number 1. Pretty straightforward. Let's get into problem number 2. We're going to be talking about finding an inverse and then doing the function test to determine is the inverse also a function like the original function we were given. So here's our problem. We're going to find the inverse of the given function and then determine if the inverse that we found is also a function. And the function we're given here is a quadratic equation, y equals 1 minus 2x, that whole quantity squared, plus 5. It's not in vertex form or standard form, but it's still a quadratic because we see that squared. So let's just work with it and we'll just figure out what the inverse is and then we'll determine is that inverse a function or not. So what we're going to do, so actually before I do that, I'll show you the solution already pre-written and we're going to work through this again. So as you can see, the answer is not a function, and then I'll tell you exactly why is it not a function. So the first thing I'm going to do is I'm just going to rewrite the original function we were given, y equals 1 minus 2x squared plus 5. Again, it's a quadratic, but it's not written in a form that we've seen like vertex form or standard form, which is fine. We're just going to find the inverse from this. So our first step, remember, to find the inverse is swap the y and the x. So in this case, wherever we see x, we're going to rewrite it as y, and wherever we see y, we're going to rewrite it as x. So I'm going to rewrite this y as x, put that equal sign, 1 minus 2, I'm going to rewrite this as y, squared plus 5. And now all we have to do is solve for y by isolating it. So by moving all the other numbers and all the other operations to the other side of the equation to get y by itself. In order to do that, first I'm going to subtract 5 from both sides. So I'm going to get x minus 5 equals 1 minus 2y, that quantity squared. Then what we're going to do is we're going to square root both sides because we need to undo the square that has been done to this whole expression within the parentheses. So if we square root both sides, we'll get the positive or negative square root of x minus 5 equals 1 minus, I'm not going to use a parenthesis, but equals 1 minus 2y. And keep in mind that we're including the plus or minus sign because we're taking both the principal and negative root, because in this case we're working with a quadratic. So when we have quadratics, we form a nice parabola when we graph it, obviously. Here, as you can see, the inverse and all the other examples we've worked with, when we're finding the inverse of a quadratic, it's going to be a square root, because a square root you can think of as like the opposite of a quadratic, and the inverse is the opposite of the original function. So if we're finding a square root, as I've shown you in previous videos, this regular square root function looks something like this when I'm drawing at the top of the screen. It'll look like half of a parabola but lying on its side. So what we need to do is include positive or negative so that we consider the other half as well, because a parabola has two halves, whereas if we just write the principal square root function, we're only going to consider one half. So this would be a hyperbola because we're considering both the principal, and we're considering the negative square roots. So that's why I wrote the plus or minus sign. So let's continue finding the inverse. I'm going to continue up here. Our next step is, we're trying to get y by itself. So let's subtract 1 from both sides. So we're going to have positive or negative the square root of negative 5 minus 1 equals negative 2y. Now, to finally get y by itself, we're going to just divide both sides by negative 2. So we're going to get y equals, well, the negative sign in front of the 2 really doesn't make much of a difference, because what happens is we're considering this positive or negative root, so I wouldn't worry much about it. So then we end up getting positive or negative the square root of x minus 5 minus 1 over 2. And then this would be our inverse. We can also rewrite it as f of negative 1, f to the power of negative 1, which is also inverse notation. F to the power of negative 1x is equal to positive or negative square root of x minus 5 minus 1 over 2. And now we finally got to determine, is this a function or not? Well, you should already be able to tell this is not a function. You might be wondering, why is that? Well, there are two reasons. If you look at these graphs I drew up here, this is a hyperbola. This is what this would look like if we graphed it on the coordinate plane. This doesn't pass the vertical line test, because if I draw vertical lines like this, these vertical lines will hit the graph in more than one place for each x value. That means that multiple y values are corresponding to the same x value, so multiple outputs can be gotten from the same input, which does not imply that this is a function. So this is not a true function. In addition, the domain is not negative infinity to positive infinity. So there are breaks in the domain, because wherever that vertex of the hyperbola is, if you think about it, all the points that fall to the other side of that vertex, whichever way that the hyperbola is facing away from, those points don't belong in the function. They're all undefined. They don't have values. Therefore, the domain is also not continuous. So again, this is not a function. Alright, so moving on, here's our third problem. We're going to find another inverse, and we're going to graph. So it's very similar to the first problem, but this one's going to be a bit more difficult. So here's the problem. We're going to graph the relation and its inverse. The relation we've been given, well, in this case, it's a function because it's a quadratic, but in this case, the quadratic is y equals 3 minus 2x at quantity squared minus 1. So what we're going to do is we are going to find the relation. We're going to graph the we're going to find what the inverse is, and then we're going to graph both the original function and the inverse on the coordinate plane. So here's your solution already pre-written. This is all the work that you have to do before you prepare to graph. And then here are the graphs of both the original function and then the inverse. So we're going to go over how we solve this. So what we're going to do first is we are going to just rewrite the original function we've been given. So y equals 3 minus 2x squared minus 1. Before I even start solving it, I do want you to consider, what does this look like? Because this is a quadratic, and it looks very similar to vertex form. Y equals a times x minus h squared plus k. A was our stretch or compression factor. X was obviously just x. We would input whatever x value we had. H was the x coordinate of the vertex of the parabola. And then k was our y coordinate of the vertex of the parabola. Usually we translated it up or down from the origin if k was not equal to 0, because the parent parabola's vertex is at the origin 0, 0. So h and k pretty much determine how we're translating that parent parabola, and then a would determine, are we stretching it, are we compressing it. So those are the things I want you to keep in mind. We've already gone over this in our quadratics unit, but it's appearing again, so you can see how the concepts we previously learned have applications later on in the course. So anyways, we already, like I said, we know that the vertex is equal to hk. H and k from vertex form. So the vertex, the x-coordinate of the vertex is h, the y-coordinate of the vertex is k. And now we have to the reason I'm bringing this up is because what we're going to end up doing is, to save ourselves time, we're pretty much going to be taking this function, we're going to be making an xy table for it with 5 coordinates, and then instead of finding the equation of the inverse, all we have to do is just flip the x and y coordinates, and then we can find the coordinates of the inverse. We don't need to find the actual equation of the inverse, because here all we've been told is just graph the relation in its inverse. We're not told to find the actual equation of the inverse. So the reason we're finding the vertex is because if you remember from our graphing quadratics and parabolas, what we want to do is we want to always get 5 points that belong to that quadratic so that you can sketch a nice curve. If we get 3, it looks a bit like a v, like an absolute value function, but if we get 5, we can actually sketch a nice curve connecting those points. Obviously, our center point, we want it to be the vertex, so our graph looks balanced. So what we do is we find the vertex, and then we find 2 points on both sides of the vertex so we can get a nice balanced graph that demonstrates our ability to locate where on the coordinate plane the function's graph is. So that's what we're trying to find the vertex. We're going to find the vertex, and then we're going to find 2 points with 2 points that are greater and 2 points less than the vertex. So 2 points that fall on the left, and then 2 points that fall on the right, and then all we'll do is just flip those x and y coordinates to find the coordinates of the inverse. So in this case, to find what we're trying to do is pretty much find h and k from the original function we've been given. K should be pretty obvious. It's this -1 sitting out here. So k is equal to -1, but h is a bit more tricky, and this is the logic I used to find what h was. So I just focused on what was in this set of parentheses. In this case, a is equal to 1, so we don't need to worry about that. Right now we're focusing on this 3 minus 2x. So to find that, I focused on the 3 minus 2x. What I did next was I rearrange this, because if you look at what's in the parentheses in vertex form, it's x minus h. In this case, it's almost like we have h minus x. So I rearranged this to rewrite it as -2x plus 3. Then when you look at vertex form, x doesn't have any coefficient. So we need to get rid of this -2. So we've got to pull it out of this linear binomial here. So if we pull it out, we get -2 times x minus 3 over 2. So that looks a bit more like vertex form. So now we're going to focus on this -3 over 2. And as you can see, it's a -3 over 2. It's minus 3 over 2. But in this case, we also have a negative h. So to find what h actually is, we're pretty much going to multiply whatever is in the set of parentheses by -1 or find the opposite. So in this case, h is going to be equal to 3 over 2. So our vertex is 3 over 2, -1. So what I'm going to do is I'm going to make xy tables. So this is going to be f of x, which was our original function, the quadratic we just worked with, xy, and then here is going to be our inverse. Again, we're not finding the actual equation of the inverse, but we're just going to flip the points that we found for the original function. So what we're going to do first is I'm just going to put 3 over 2, -1 in the middle. I'm going to pick 2 points greater and 2 points less than that. So 3 over 2 is pretty much 1/2. So I could pick 1, and if I do pick 1, I have to pick a x coordinate that is half greater than 3 over 2, which is 3 over 2, which is 1/2, plus 0.5 is equal to 2. So that would work. And then I can pick 0 up here, which is just 1 less than 1. And then if I pick 0, I have to pick 3 because I'm adding 1 to 2 as well. So hopefully you see how that works. And pretty much all we're going to do is we're going to plug these values back into the original equation to find the corresponding y coordinate. So if I plug 1 in, I get 2 times 1 is equal to 2, 3 minus 2 is 1, 1 squared is 1, and 1 minus 1 is equal to 0. Same thing with 2. 2 times 2 is 4. 3 minus 4 is equal to -1. -1 squared is 1. 1 minus 1 is equal to 0. So that's why we picked points that are equidistant from the vertex, so that the y coordinates are identical to each other. Then if we look at 0, if we plug 0 in, 2 times 0 is just 0. So 3 minus 0 is 3. 3 squared is 9. 9 minus 1 is 8. And then if you plug 3 in, 3 times 2 is 6, 3 minus 6 is -3, -3 squared is 9, and 9 minus 1 is equal to 8. And then to find the points of f inverse, all we have to do is just flip the x and y coordinates. So the x coordinates are going to be 8, 0, -1, 0, and 8. And the y coordinates are going to be 0, 1, 3 over 2, 2, and 3. So f of x is going to be our regular parabola, and then f inverse is going to be our hyperbola, because the opposite of a quadratic is going to be a square root function. So now I'm going to pull up a graph, and then I'm going to erase what we just did so that we can actually graph this. All right, so now that that's erased, let's start with a fresh graph, and then let's go over how we would graph this. So off to the side, I have the xy tables that we made for our original function f of x and the inverse, f inverse. I'm going to use those coordinates to show you how we're just going to graph these. It's simply a parabola and a hyperbola, so nothing too complicated. So our first point we're going to start with our function was 0, 8. So that would be here, and then we would go up 8 on the y-axis. Our second point was 1, 0. So we're going to stay on the x-axis, and then we're going to go right 1. And then our third point was 3 over 2, which is 1/2, which would be right here, -1. So our vertex would be down here. Our fourth point was 2. Our fourth point was 2, 0. So we're going 2 right on the x-axis, and we're not moving from the x-axis. And then our last point was 3, 8. So we're going right 3 and up 8. So this is going to be our original function, our parabola. So you can just connect those points. And then the next graph we're going to work with is the inverse. So the first point of the inverse is 8, 0. So we're going right 8, but we're not leaving the x-axis. Our next point was 0, 1. So we are staying at the origin, but then going up just 1 point. Our third point was -1, 3/2. So -1's over here, and we're going to be up here at 1.5. Our fourth point is 0, 2, so we'd be up here. And then our final point is going to be 3, 8. Sorry, 8, 3, my bad, 8, 3. So we'll be up here. So we can just connect these points, and you can see this is a hyperbola. So it's a double-sided square root function if you want to think of it like that. So I'm just going to make this a bit more curvy. And then that's your parabola and your hyperbola. Again, I want you to take into consideration that this is pretty much the original function, which was the quadratic, is pretty much just reflected across y equals x, that line, that axis of symmetry, to give you the graph of the inverse. All right, everyone, thank you for joining me for this lesson. I'm going to postpone problem number 4. We'll put it in the next lesson because there are a few other things I do want to go over in that next lesson. So stay tuned for part 2. We're going to be doing some more practice problems and then wrapping up inverse practice problems and the whole inverse lessons series. I hope you enjoyed the video, and if you did, please like, subscribe, hit the post notification bell, drop a comment down below, and share using our socials. Also, check out our website and Gmail. I hope you enjoyed, and thank you for watching.